This video is going to be rather different from my usual ones. For one thing, this is really a request-based video. A student had requested me, an ex-student of mine had requested me to make a video on a technique that I had taught their class quite some time ago when I was taking a class on differential geometry. And I thought that this is an important enough thing so that I make a video explaining this to a more general audience. However, this is not really directed at a very general audience in the sense that I am going to take certain background for granted in this video. I'm not going to explain all the theorems and the proofs and so on. I'm just going to illustrate how you can use differential geometric techniques to efficiently calculate the curvature of a space or space-time as your inclination might lie. Now, I would have loved to say that if you want any of the background, you should actually go and watch some of my videos on these topics. But frankly, I have begun making videos on differential geometry comparatively recently, and at the slow pace at which I am progressing, it will take me a long time to get to these topics. So, if you already have the background in things like the torsion, curvature, and so on, and some background in differential forms, and especially how to calculate the exterior derivatives, please go ahead with this. Otherwise, if you are really interested in finding out how differential geometric techniques can speed up calculation of curvature and other geometric entities, pick up a book and study those things before you pursue this video. Of course, one might very well say that this is really not that important because you can always ask Mathematica or some other computer programming language to calculate curvature for you. But frankly, that doesn't really give you the insights. They are fine for quick calculations, especially if you have no other easy way out. However, I would like to illustrate this method where you should be able to calculate relatively complicated things with relative ease. This is not going to be an easy calculation, so please don't assume that if you are going to use some differential geometric technique, it's going to be a magic wand which sort of makes everything very easy. But if you have experience in calculating curvatures for non-trivial metrics, you would definitely appreciate how much easier it is using these slightly advanced techniques. Once again, I'm not going to explain the rationale behind these techniques. I'm just going to state the steps and show how the calculation is carried out. I will actually try to introduce the necessary background in the differential geometry videos that I am making, but given the pace, as I said, no guarantees about when that will be done. So first, quickly, the kind of background that you need for this. First of all, you need to know that in a manifold, you of course need to know what a manifold is. And you should also know that there are tangent vectors to a manifold, there are vector fields and so on. And you can define for an n-dimensional manifold a set of n vector fields which provide bases at all points. In other words, if you were to evaluate these vector fields at a point P, the values, the vectors that you get, the n vectors that you get, will provide a basis for the tangent plane TPN at that point. And along with this set of n basis vector fields, you have a dual set of basis covector fields, which in the same sense provide you with basis for TP star n. Of course, when you evaluate these covector fields at the point P, you are going to get theta 1p, theta 2p, theta np, and these are going to form a basis of TP star m. Now, a very standard relation between these two sets that are very often used is you choose theta I in such a way that theta I acting on the ej's give you functions, but the functions are very simple functions. They're delta ij. They're constant functions, constant at either 1 if I equal to j or 0 if I is not equal to j. And we all know the standard example of this. If you're using coordinates, then the set of basis vector fields del del x1, del x2, del del xn, where at any point p, del del x1 p, for example, is a tangent vector to the coordinate curve, by only varying the first coordinate and keeping all other coordinates fixed at the value which they take at the point p. And corresponding to this, you have an obvious dual set, which are the coordinate differentials themselves. So very often we will use these set of basis vectors. In fact, that's the most common thing that is done, at least in elementary physics calculations, or when we physicists typically define a vector or tensor in terms of components, and those components are typically expressed in this basis, the coordinate basis. But what I'm going to talk about actually works in other bases as well, and as you will see, sometimes using a different basis, not a basis like this, something which is technically called a holonomic basis, using a different one is often more useful or simpler. Now, the kind of thing that we are going to calculate involves things called curvature, but before we go to curvature, we need to talk about connection. I'm of course not going to talk about the full theory of connections. I will just mention that a connection del assigns to a smooth vector field x a map del x, the covariant derivative with respect to x, or directional derivative in the direction of x. At least this is a generalization of the notion of directional derivative in the direction of a particular vector that we have in ordinary calculus. Now, this is a map which actually maps smooth vector fields into other smooth vector fields. Of course, there are a lot of additional properties which has to be satisfied before you can legitimately call something a connection. These properties are basically based on making this as close to ordinary directional derivatives on Rn as possible. Now, I'm not going to talk about all those properties here. Hopefully, I will make a video on them sometime in the future, but more importantly, you can just look this up in any differential geometry textbook. What is important for us is the fact that if you take, say, one of the basis vector fields, let's say EI, and carry out the covariant derivative of that in the direction of EJ, another basis vector field, you're of course going to get a vector field. So, you should be able to expand this in terms of the basis vector fields. So, Ek, gamma k, ij, where gamma k, ij's are functions, smooth functions in particular, and these are called the connection coefficients. Of course, one way in which you can directly write down the gamma k ij's is that if you take the covariant basis vector field theta k and apply it on this, you're going to get gamma k ij. So, theta k acting on rad ej acting on ei, that's gamma k ij. Just notice the I and j here are just reversed in order in a way. That's part of the definition. Now, what we are going to calculate here, as we said, is curvature, but we need to introduce at least a definition of two essential things here. One is the torsion, T, which acts on two smooth vector fields to produce a vector field and is defined to be basically this particular vector field. And for curvature, we have a tensorial object R which, acting on two smooth vector fields x and y, does not directly give rise to a vector field, but rather an operator which would act on a vector field to produce another one. So this is basically defined to be grad x grad y minus grad y grad x minus grad x comma y. Of course, these definitions did not come out of the blue. There is a very basic reason why you need each of these pieces in the definition to produce a proper tensorial object. But once again, that's not something I'm going to go into. This is just a definition. What is important here is take T, apply it on EI and EJ, two basis vector fields. You should be able to expand the resulting vector field in terms of the basis vector fields again, and you get something which is written like this. Tkij, these are nominally, if you forget about all symmetries here, n-cube smooth functions which define what is called the torsion associated with this particular connection. Well, with R, you can go over to smooth functions, but it takes a bit more work in the sense that R acting on EI, EJ does not directly give you a vector field. This gives an operator which would act on a vector field. So let it act on another basis vector field EK. This is a vector field, so can be expanded in the basis vector fields in this fashion. R, L, Kij. That's how you define the RL Kijs, the Riemann curvature tensor components. And if you don't take into account symmetries, there are n to the 4 of them. Our job here is to try to calculate RL Kijs, not for any connection whatsoever, but for a specific kind of connection, the so-called metric connection, which are the ones which are really going to be important, at least as far as GR is concerned. So, when you have a metric connection, the basic idea is, first of all, you have a metric, that is, you have a 0 to tensor, covariant tensor of rank 2 in the older terminology, which maps two vector fields into a number. Essentially, it gives you the inner product between those two vector fields, and you can of course expand this out in your basis in this particular fashion. And GIJs are the so-called metric functions which we are used to looking at. In fact, as physicists, we are perhaps more used to looking at this in the form ds squared, the invariant length between 2 points, is given by dxi dxj. This is essentially the same thing as saying that the metric is this tensor given by these components. Of course, here, instead of choosing any basis, we have chosen to actually expand this out specifically in the coordinate basis. And associated with the metric, you have a connection, and the metric connection is one in which you have grad x, the covariant derivative of the covariant tensor G, to be 0 for all x, and this imposes a huge constraint on the connection. Also, you demand in a Riemannian metric that torsion is 0. In fact, torsion being 0 tells you that at least if you are using the coordinate components, then gamma k ij is symmetric in the lower two indices. That's not a general statement about all gamma k ij's. It's only a statement when you are using a coordinate basis. And in this case, you can actually calculate the gamma k ij's. Well, this is not really a definition. I should really use equal to here. This formula that I'm going to write down follows essentially from this. Is GKL times what are called the Christoffel symbols of the first kind, ij comma L within a curly bracket, We often refer to this as Christoffel symbols of the second kind. That's specifically for a metric connection. And this is given by half GKL times del G IL del XJ del G JL del XI minus del G IJ del XL. Now, the torsion coefficients that we talked about earlier can also be written down in terms of the metric components. In fact, they will always work out to be 0. But say the R, IJKLs, they can also be written down in terms of the metric components, but it's perhaps more convenient to write them down in terms of the Christoffel symbols themselves. And the standard formula that we have for this is given by del x k gamma IJL minus del x L gamma IJK plus gamma MJL gamma IKM minus gamma MJK gamma ILM. And torsion being 0 has a consequence, as we already mentioned, that at least in the component basis you have. Now, this is the background that we assume that everybody already is aware of. So this was just a sort of recap, all of this. But you must realize that if you are given an arbitrary metric, that is, you are given the functions Gij, n square in number, of course they are symmetric, so it's really n into n plus 1 by 2 rather than n square independent functions, and then asked to calculate the curvature. This formula looks pretty formidable. More importantly than that, there are a huge number of terms to be calculated here, and very often figuring out which ones are non-zero beforehand is quite a difficult task. So you end up calculating a lot of terms. If your metric is simple enough or has some special symmetries, many of these terms might be 0, but unfortunately you will not be able to see that they are 0 beforehand. So you will end up calculating a huge number of terms, maybe to find out that at the end, only a few survive. What we are going to talk about today is a more efficient way of calculating this using something called Cartan structure equations, which are consequences of differential geometry. Now, in order to be able to use this, we first need to introduce certain forms. Let me remind you, I am assuming that a basic knowledge of differential forms is something that the audience has here. Firstly, we need n square 1 forms. These are called the connection 1 forms. That's just a name. The way you define them is the following. You define them using the symbol capital gamma, which of course tells you that it's connected to the gamma ijk's, and the connection is very simple. It's gamma ijk theta k. Of course, sum over k is implied here. So for each pair of values I and j, you have one such connection 1 form. Then we move on to torsion, and here you have 2 forms, but only n in number. These are torsion 2 forms. The way you define them are the following. You have one index ti, and that's ti jk, theta j, wedge theta k. This is the exterior product of the 2 basis vectors, basis covector fields. And then you have n square 2 forms describing the curvature, curly r I j, which are, okay, there's a half here and a half here as well. This half is simply to make life simpler later. I j k l theta k wedge theta l. Now, the reason why these forms are so useful is actually that there are equations which tell you how to calculate these entities directly. So that once you've calculated Ti and Rij, you can just expand them in the basis. In fact, they will come usually expanded in the basis. And from that, you can immediately read off what the coefficients are going to be. And these coefficients are going to give you the torsion coefficients and the curvature coefficients. Once again, if we are dealing with Riemannian geometry, then the torsion coefficient will be identically 0. You really have to worry then only about this one. But in a general geometry, you would have to worry about both of these. So, the equation which actually tells us how to do this trick or how to do this magic are the following. These are Cartan structure equations. The first one expresses Ti in terms of theta I. It's the exterior derivative of theta I. Remember, Ti is a two form. Theta I is a one forms. D of that are of course two forms. Plus the wedge product and the second structure equation actually tells us what curly Rij. How is it related to the gamma ij's? Is d gamma ij plus gamma ik wedge gamma kj. Of course, sum over k, etc. are all implied here. I am just stating this without proof. Consult a differential geometric text if you want the proof. But let me now show you how you could use these equations and calculate the curvature, that is the coefficients that you have of this curly Rij when you expand that in the theta k wedge theta l basis in a rather efficient fashion.